Welcome to the first installment of Advanced Chemistry Lectures and the very first tutorial on electron counting and transition metal complexes. And so the goal of this tutorial is for you to be able to electron count any transition metal complex you encounter, whether they're very basic octahedral molecules like the moly compound showed in the upper left, dinuclear metal complexes featuring metal-metal bonds like the manganese compound shown on the right, compounds that feature bridging ligands like the chloride-bridged rhodium dimer shown on the left, or complexes that act as olefin metathesis catalysts like the tungsten-6 compound shown in the upper right. And so the electron counting is extremely important because this also dictates structure, dictates what kind of mechanism of substitution may occur at transition metal centers, and kind of guides what type of organometallic processes like oxidative addition and reductive elimination are possible. And so there's a couple of different ways to electron count transition metal complexes. The method I like or prefer the most is the donor pair method because I believe it is the most intuitive method. It also allows you to get the metal oxidation state, the d electron count, and the total electron count directly. And so in order to use this method, what we're going to do is we're going to treat the metal as the Lewis acid and the ligands as the Lewis bases. And so you've encountered this type of concept of forming Lewis acid, Lewis base adducts back in general chemistry, in which you took compounds that are Lewis bases such as ammonia, which features an sp3 hybridized nitrogen center, which is a lone pair in the fourth sp3 hybrid orbital, and that can donate that electron pair to the empty 2p orbital on the sp2 hybridized boron center of BH3, forming the Lewis acid, Lewis base adduct ammonia borane. And so we're going to treat metal complexes just like this. And so if you think about it, if you wanted to go back from the Lewis acid base adduct of ammonia borane, what you would want to do is take the 2 electrons from the nitrogen boron bond and give them directly back to nitrogen, and that would lead you to have the reactants on the left side of the arrow. We're going to take the exact same approach with transition metal complexes. We're going to give the electrons back to the Lewis base, in this case trimethylphosphine. When you do that, you then arrive at having your free trimethylphosphine now non-bound to the metal center. And so when we're considering our ligands, what we always want to consider is that the donor atom in 99% of cases must have an octet. And we see here that our phosphorus atom here does have an octet. What we then want to figure out is the charge on this donor ligand. And so in order to calculate the charge, we're going to calculate the formal charge on the donor atom, in this case phosphorus. And so we know phosphorus has 5 valence electrons, it has 2 lone pair electrons, it has 3 PC bonds. 5 minus 2 minus 3 equals 0. So the phosphorus atom itself here has no charge. PME3 is a neutral 2-electron donor. And what that means is, since that the moly compound has no charge, that the moly complex must be moly 0, which is D6. Note that this is different than general chemistry. In general chemistry, you learn that moly had a 5s1, 4d5 configuration. In transition metal chemistry, once we get there, we're no longer counting s electrons. Our s electrons are going to be counted as d electrons. And so moly 0 is not 5s1, 4d5. Moly 0 is d6. Similarly, if you look at your periodic table, take iron, for example. Iron is not 4s2, 3d6. Iron 0, is d8. And so now, if we come back to the problem at hand here, this moly compound, we have moly 0, which is D6. We have 6 PME3 donors. Each are donating 2 electrons. And so if we have moly 0, which is D6, we have 6 PME3 donors donating 2 electrons each. That's 12 electrons due to the ligands. 6 plus 12 equals 18 total electrons. And so let's now see if we can apply this very basic method to some other transition metal complexes. This tungsten compound is very similar to the moly compound on the previous page. If we give the electrons back, we have a carbon monoxide donor. Carbon monoxide is a neutral 2-electron donor. The carbon atom features a formal negative charge, but the oxygen atom features a normal positive charge. Why? Well, carbon has 4 valence electrons, minus 2 lone pair electrons, minus 3 bonds is -1. Oxygen, on the other hand, has 6 valence electrons, minus 2 lone pair electrons, minus 3 bonds, equals +1 overall. The negative and the positive cancel out, and carbon monoxide is a neutral 2-electron donor. That means that the tungsten center then is tungsten 0, which is D6. You have now 6 2-electron carbon monoxide donors for 12 more electrons. 6 plus 12 electrons, this is an 18-electron compound. Now let's go over here to the cobalt compound in the upper right-hand corner. If we give the electrons back to each phosphorus donor of the bidentate ligand, notice that that is really just a glorified PR3. It is a phosphorus center with 3 PC bonds and a lone pair on the central phosphorus. These are neutral 2-electron donors as well. Same with the carbon monoxides. However, the hydride, when we give the electrons back to H, we now have a hydride. A H atom with 2 electrons is negatively charged. So in order to balance out that negative charge on the hydride, cobalt must be cobalt 1. Cobalt 1 is D8. You now have 5 2-electron donors. For all 5 of the ligands bound to cobalt are, again, 2-electron donors. That donates 10 more electrons for an overall 18-electron count. All right, let's move to the iron compound on the lower left. Notice if we give the electrons back to the 2 phosphine donors, again, this is a glorified PR3 with a lone pair on phosphorus. Those are neutral 2-electron donors. We know that hydride is an anionic 2-electron donor, and CO is a neutral 2-electron donor. However, the nitrogen donor here might be a little confusing. If you give the electrons back to the nitrogen, you might suspect that your nitrogen looks like this. That would be a nitrinium ion. That is not what we have. There is an implied and present lone pair on this nitrogen atom. And so what you have here is, notice that the nitrogen now has an octet. This is an Nr2 minus. This is an anionic amido ligand. So we know now that since this nitrogen is anionic, that the iron center must be iron 2. Iron 2 is D6. You have 5 2-electron donors. 5 2-electron donors contributes 10 more electrons for a total of 16 electrons. Moving to the rhodium compound. We know now that all of these phosphines are actually neutral 2-electron donors. We give the 2 electrons to chlorine. We get chloride, which is a -1 2-electron donor. What that means then is that the rhodium center is rhodium 1. Rhodium 1 is D8. You have 4 2-electron donors to rhodium. That contributes 8 more electrons. That gives you a 16-electron compound. If we come over to the platinum compound here on the bottom right-hand corner, if we give the electrons back to these 2 amine donors, I'm going to do it for the primary amine. If R is H, it is just this ammonia ligand, and so you can see that they are exactly the same. They are nitrogen featuring 3 bonds and a lone pair. That is a neutral 2-electron nitrogen donor. If we give the electrons back to OH, you should know that this is the hydroxide anion. This is an anionic 2-electron donor. We know that chloride is -1. Chloride is -1. The other hydroxide is also -1. That means that platinum must be platinum 4. Platinum 4 is D6. You have 6 2-electron donors. That contributes 12 more electrons for now a total of 18 total electrons. And if we click ahead here, you can see that all of my answers are correct. We have an 18-electron tungsten compound, an 18-electron cobalt, 16-electron iron, 16-electron rhodium, and 18-electron platinum compound. So got a couple more challenging examples here. Here's a moly compound on the left. Notice that these nitrogens, again, are Nr2 minuses. They are amido donors. And so this is a nitrogen. If you give the electrons back, you put the second lone pair on nitrogen. And so those are 2 anionic ligands. We know that hydride is also -1, but how are we going to deal with this 3-membered ring piece that's connected to moly? And so if we give the electrons back, you get a unit that looks like this. There is a carbon bound to 2 methyls, bound to the nitrogen featuring a lone pair. That means it is anionic. Carbon has 4 valence electrons, -2 lone pair electrons, -3 bonds is -1 overall. This nitrogen center also has 2 lone pairs and an arrow group. It is also an anionic donor. Again, remember there is a lone pair on this nitrogen. You give the electrons back. You form another lone pair on the nitrogen. It has an octet. So all of the donors to the moly center are anionic. This gives us a moly 5 center. Moly 5 is D1 plus 5 2-electron donors. That's 10 more electrons for 11 electrons total. Anytime you get an odd electron count, I would suggest double checking to make sure you are correct. I am correct in this case, but oftentimes an odd electron count means you made a kind of a careless error. If we go now to the zirconium compound, notice you give the electrons back to the apical nitrogen. This is a nitrogen featuring 3 NC bonds and a lone pair. That is a neutral nitrogen. However, all of the nitrogens in the equatorial plane contain a lone pair that is not drawn there. When you give the electrons back, you again get a glorified Nr2 minus. These are amido donors. They are all anionic, so -1, -2, minus 3. If you give the electrons back here to the phosphorus donor, it also has an implied lone pair on the phosphorus center. This is a phosphido, so this is a heavier analog of the amido. It is also a -1 ligand. We have 4 -1 ligands, so this is zirconium 4. Zirconium 4 is D0. You have 5 2-electron donors. That contributes 10 electrons total. 0 plus 10, this is a 10-electron compound. If we now start to consider molecules that feature a metal-metal bond, how are we going to handle this? How are we going to treat these metal-metal bonds? Well, we're going to treat these metal-metal bonds as being purely covalent. So what that means is, if we consider the manganese compound on the left, the manganese-manganese bond is a single bond, and so there is 2 electrons associated with it. Notice that all of the ligands bound to the moly are all carbon monoxide. Carbon monoxide, remember, is a neutral 2-electron donor. When you give the electrons back to carbon monoxide, you get CO, which looks like this. Again, a neutral 2-electron donor. And so we know that it is manganese 0. Manganese 0 is D7. We're going to give 1 electron to each metal for the metal-metal bond. So plus 1 electron, let's say to the manganese center up top, plus 5 CO donors, each contributing 2 electrons. That's 10 more electrons. So 7 plus 1 plus 10. This is an 18-electron compound. All right, what about the moly compound on the right? Well, this features a moly-moly triple bond, and a triple bond then has 6 electrons associated with it. So if we kind of stitch a double dotted line down here and split the moly-moly compound in half, the triple bond now will contribute 3 electrons to each moly center. But let's now figure out how we're going to assign the oxidation state to moly. If we give the electrons back to these oxygen donors, notice that these are just terbutoxides. Terbutoxide is an anionic donor, and so this is anionic, anionic, anionic. This is moly 3. Moly 3 is D3, plus 3 electrons due to the triple bond gets you up to 6 electrons, plus 3 2-electron donors for the alkoxides is 6 more electrons. 3 plus 3 plus 6 is 12 total electrons. This is a 12-electron compound. All right, well, what are we going to do about bridging ligands? Well, bridging ligands fall into 2 categories. Those with extra electrons, and by extra electrons, I mean they're going to have a lot of lone pairs, and this kind of corresponds to bridging chlorides, which are always represented, the bridge is represented by the mu notation, and those without extra electrons, like bridging hydrides. And so let's take a look at this rhodium dimer shown here on the left with bridging chlorides. And so if we take our same approach and we're going to give our electrons back to chlorine, give your electrons back to chlorine, you get 2 distinct chloride donors. Both chloride donors are -1. And they're both bound to the rhodium center. And so they have, what I mean by extra electrons is there's extra lone pairs. And so the chlorines, they are each -1, and they can contribute 2 electrons to each rhodium center. So there's 2 electrons to 1 rhodium center, 2 electrons to 1 rhodium center, 2 electrons, 2 electrons. However, when we're calculating the oxidation state, there is 2 chlorides, and so that's -2 overall. We have 2 rhodium centers. We haven't identified the oxidation state yet, but the complex is overall neutral, and so this means X equals +1, so it is rhodium 1. Rhodium 1 is D8, and so now that we have D8, we have 4 2-electron donors. That contributes 8 more electrons for 16 electrons total. All right, and so in general, when I approach these problems, what I do to try to make it quick and easy is that I always, when I get a dimer, is I cut it in half, and I'm cutting it in half representing by this blue line that I've drawn down here. So what I do is I kind of consider half the molecule, let's say this half here. And so notice that that half here has only 1 chloride associated with that rhodium. And so that means that it is rhodium 1. Rhodium 1 again is D8. However, I know that the chlorides have extra lone pairs, and so 2 electrons in each direction for the chlorine contributes now, if we're talking about this rhodium center, 2 electrons for this rhodium chloride bond, 2 electrons for this one, 2 electrons to CO, 2 electrons to CO is 8 more total electrons for a 16 electron compound. All right, how about the niobium compound on the right? So again, I'm going to take my approach of cutting the dimer in half. So I'm only going to look at this half here to assign the oxidation state. I know chloride is -1, -1, -1, -1, -1. So it's niobium 5. Niobium 5 is D0. I know that each of these, this is 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. I didn't forget that chloride has extra lone pairs. It can donate in both directions. So I have now 6 2-electron donors contributing 12 electrons. If I have a D0 center, this is overall a 12-electron compound. All right, so what we do if we don't have extra electrons, and so a textbook case of not having extra electrons is hydride. And so if we take a similar approach to the hydride bridge copper compound shown here, if we give the electrons back, you have hydride. You have this, a H with a lone pair, it is -1. It is not an H with 2 lone pairs and is 3-. That is not the case. And so what actually is going on here is you have a copper hydride in which it is now bridging. You only have 2 electrons at the hydride, and what this is a 3-center, 2-electron multi-center bonds, which I will discuss in a later tutorial. But again, we're going to take the same approach, though, of actually cutting the dimer in half. If you cut the dimer in half, you can then assign the oxidation state. So I'm only going to pay attention to this side over here. And so there's only 1 hydride on that copper. So it's copper 1, which is D10. You can either count this in one of 2 ways. I'm going to count it by cutting it in half, that this hydride right here is going to donate 2 electrons here, while this hydride here is going to donate its 2 electrons here. You can take an alternative approach in which you think about each hydride donating 1 electron to each copper center, or, like I've done here, you take the hydride, 2 electrons go to 1 copper center, while the other hydride donates 2 electrons to the other. So now I have 2 electrons due to the bridging hydride, plus these phosphines here are both neutral 2-electron donors. So 2 electron donors, 10 plus 2 plus 4. This is a 16-electron compound. What about this iron compound featuring bridging carbon monoxides? Again, you know carbon monoxide has a Lewis structure that looks like this. And so that carbon atom has only 2 electrons on it. So you have to think about it's giving 1 electron to one iron center and 1 electron to the other iron center. And so if I'm going to electron count this compound, all the donors are neutral. They are all carbon monoxide. So it's iron 0, which is D8. If I look at the terminal carbon monoxides, there are 3 of them. So 3 that are 2-electron donors gives me 6 more electrons. You then have 3 bridging carbon monoxides, so 1 electron to this iron center, 1 electron, 1 electron. So 3 electrons due to bridging carbon monoxides, and then remember we have an iron-iron bond here, so 1 more electron goes to the iron center on the left, 1 electron on the left. So I have 8 plus 6 is 14, plus 3 more is 17, plus 1 more, this is an 18-electron compound. And so I've tried to show here how I actually broke this up. And so remember that now we have 1 electron goes this way, 1 electron this way, the iron-iron bond, 1 electron in each direction, 1 electron in each direction, same thing for the other COs. So both iron centers are iron 0, they are D8, they are 18-electron compounds. All right, this brings us then to combining parts 1 through 3. And so we had simple 2-electron donors like phosphines. We then encountered metal-metal bonds, and then we encountered bridging ligands. And so if we take our palladium compound here shown on the upper left-hand corner, I'm going to cut the dimer in half. So I'm only going to look at this, let's say left half, to assign the oxidation state. So this is palladium 1. Palladium 1 is D9. I have a palladium-palladium bond, so I'm going to add 1 more electron. If I give the electrons back to each iodide, I have iodide. Iodide has a Lewis structure that looks like this, and so it can give electrons, again, in both directions to both metal centers. And so then I have two iodides, each contributing 2 electrons. So that's 4 more electrons, plus the phosphine, 2 more electrons. This gives me 16 total electrons at the palladium center on the left. The palladium center on the right is exactly the same. Let's move to this moly compound on the right. And so now if I cut this dimer in half to get the oxidation state of the moly center, I know I have, if I give the electrons back, that's methoxide. So methoxide has a Lewis structure that looks like this. Notice that it has extra lone pairs, so it can give to one moly center and give to another moly center simultaneously, so 2 electrons in both directions. But it is, again, it is a -1. It is a alkoxide. This is -1, chloride is -1, -1, -1. And so I then have a moly 5 center. Moly 5 is D1, add 1 electron for the moly-moly bond. That gets me to 2 electrons. The methoxides can give 2 electrons in both directions. So you have 2, 4, 6, 8, 10, 12. You have 6 2-electron donors. That contributes 12 more electrons. 2 plus 12, this is a 14-electron compound. How about this tantalum compound shown in the lower left-hand corner? One of my favorite compounds. I was a little bit lazy in drawing this, so I screenshotted where it was reported in this Accounts of Chemical Research paper. And so I'm going to cut the dimer in half here, and I'm going to treat the hydrides as the top 2 here giving 2 electrons to this tantalum center. 2 electrons each, I should say, while the bottom 2 hydrides give 2 electrons to the tantalum center on the right. And so when I cut the dimer in half again to get the oxidation state, the hydride is -1, the other hydride is -1. Notice that these nitrogens, they have lone pairs already on them. When you give the electrons back, it is a glorified Nr2-. They are amido donors, while the phosphine is a neutral 2-electron donor. And so again, the nitrogens are minus. And so for this tantalum center, there are 4 minuses. The overall complex is neutral, so this is tantalum 4. Tantalum 4 is D1. Notice that you have a tantalum-tantalum bond, so you're going to add 1 more electron to the tantalum center. I said I'm going to count 2 electrons this way for each hydride. So I have now 4 electrons due to the bridging hydride. So 2 bridging hydrides, counting the electrons in one direction, is 4 more electrons. The other 3 are 2-electron donors, both nitrogens and the phosphine. That's 6 more electrons. So 1 plus 1 is 2, plus 4 is 6, plus 6 more. This is a 12-electron compound. And so I've shown here, though, on the right, kind of the alternative counting method in which you can think about the hydride donating 1 this way, 1 this way, 1 this way, and 1 this way, and the other hydride donating 1 this way, 1 this way, 1 this way, and 1 this way. The bottom line is in both cases you get a 12-electron compound. Both tantalum centers are tantalum 4, which is D1. All right. Start to get increasingly more complicated. We now tackle organometallic ligands or organometallic fragments that can donate lots of electrons. Some donate just 2, but some can donate up to 6, or the most common ones can donate up to 6. And so here we have 2 anionic 2-electron donors. We have a metal phenyl unit, and so if we give the electrons back, notice that we get a C6F5-, and so this position now is a lone pair, not a hydrogen. And so this is C6H5-, and so that is an anionic 2-electron donor. This is methyl-, which is also an anionic 2-electron donor. And so now can we apply this to actually assigning the total electron count to these 2 platinum compounds? Again, if we give the electrons back, you give the electrons back, give the electrons back, give the electrons back. Notice that both of these phosphines are neutral 2-electron donors. Here we have now our C6H5-, so this is a -1. Chloride is -1. This is platinum 2. Platinum 2 is D8. 4 2-electron donors contribute 8 more electrons. This is a 16-electron compound. Notice that this platinum compound is also going to be a 16-electron compound. When you give the electrons back to this pyridine fragment, you get pyridine. Pyridine is a neutral 2-electron donor. That nitrogen is neutral and it has an octet. You give the electrons back here, you get a nitrogen that has 3 bonds to carbon and a lone pair that is also neutral. Here there's an implied lone pair on this nitrogen. This nitrogen also has a lone pair. That doesn't really matter though. When you give the electrons back, you get this unit here. You get a 5-membered ring in which this nitrogen center has 2 lone pairs. That is now anionic. So that is an anionic donor. The methyl is anionic. It is then platinum 2. Platinum 2 is D8. You have 4 2-electron donors contributing 8 more electrons for a 16-electron compound. All right, but we have other organometallic fragments that are typically a little bit more confusing and can feature up to, the most common ones can feature up to 6 electrons. And so we have eta-2 olefins, eta-3 allyls, eta-5 CP, and eta-6 benzene. And so eta-2 just refers to the fact that the donor has actually atoms that are next to one another, they're contiguous, and they're all bound to the transition metal center. And so 8 of 5 again in CP represents the fact that all 5 carbon atoms are connected and all 5 carbon atoms are bound to the transition metal center. But let's first approach the 8 of 2 olefin. An 8 of 2 olefin is a neutral 2-electron donor, which seems maybe a little bit counterintuitive, and you can't really take the approach of giving the electrons back. What you have to realize is that the pi bond on the olefin, drawn here, is actually donating in a sigma fashion. Here's the acceptor orbital on the metal. It is donating 2 electrons of the pi bond to the transition metal center. It is a neutral 2-electron donor. The 8 of 3 allyl, on the other hand, is an anionic 4-electron donor. So how is this C3H5 minus piece an anionic 4-electron donor? Well, what's really going on here is this swoop represents a delocalization of electron density. So there's 2 competing resonance structures shown here, in which you have an olefin bound as a neutral 2-electron donor and a carbanion bound as an anionic 2-electron donor. So if I gave the electrons back to that position, notice I would get this. That is an anionic 2-electron donor. So allyls are counted as anionic 4-electron donors. 2 electrons due to the anionic carbon at this position, and then 2 electrons that are neutral due to the bound olefin. When we get to CP, this is an anionic 6-electron donor. It is a 6-pi electron aromatic system. The best way to think about it as a 6 electron donor is that one valid resonance structure is shown here. Notice that it has 2 olefins. You can think of that contributing 2 and 4 electrons, followed by a carbanion donating 2 more electrons for a total of 6, the negative charge as well. While benzene, on the other hand, you can think of it as having essentially 3 olefins. We know that this is fully delocalized, but if you have 3 olefins, each contributing 2 electrons, that's now a neutral 6-electron donor. So now let's count some transition metal complexes featuring these organometallic fragments. And so I have 3 drawn here. I'm going to start with the cobalt compound on the lower left-hand corner. So CP we know is an anionic donor. PME3 we know is a neutral donor. And we know an olefin is a neutral donor. And so to balance the charge, we know that this must be cobalt 1. Cobalt 1 is D8 plus 6 electrons due to the CP plus 2 more 2-electron donors that are both neutral. 8 plus 6 is 14, plus 4 more. This is an 18-electron compound. We have a chloride-bridged palladium allyl here. Again, in order to calculate the oxidation state, what you're going to do is cut the dimer in half. So if we kind of consider this left-hand side here, notice that we have an anionic chloride. Sorry about that. We have an anionic chloride and an anionic allyl. And so what we know is this must be palladium-2. Palladium-2 is D8 plus 4 electrons due to the allyl. Remember, the allyl is an anionic 4-electron donor. The chloride gives 2 electrons. The other chloride, remember, has extra lone pairs, and so it also contributes 2 electrons, so 4 more electrons for now a total of 16 electrons. What about the ruthenium compound featuring the functionalized benzene shown in the upper right? Well, again, we know benzene is a 6 pi electrons aromatic. It contributes 6 electrons to the ruthenium center. Chlorides we know are each -1. The phosphine itself is neutral, so I'm going to count it over here. So we know then that it is ruthenium-2. Ruthenium-2 is D6. It has 3 2-electron donors, the phosphine in both chlorides, contributing 6 more electrons, plus 6 more electrons from the benzene, gives us 18 total electrons. All right, and so this then moves us to some more compounds. And so these compounds we're going to talk about are ligands that commonly form multiple bonds to the transition metal center. And so we've kind of been dealing with largely with compounds that just form a single bond to a transition metal center, but there are complexes that form multiple bonds to the transition metal center. And as you know, single bonds we count as 2-electron donors. As you can imagine, double bonds are then 4, and then triple bonds are 6. And so let's practice. All right, well, nitridos, which are these terminal species shown here, if you give the electrons back, so notice you're giving 6 electrons to the nitrogen, which already has a lone pair, and so you get a nitrogen with an octet. That is a 3 minus 6-electron donor. And so if we count the moly compound on the right here, remember that these nitrogens all feature a lone pair that's not drawn. When you give the electrons back, you have a nitrogen that has a tert-butyl and a xylyl on it with 2 lone pairs. These are anionic. So each nitrogen here is anionic. The nitrido is 3 minus. That means the moly compound must be, or the moly center must be moly 6, which is D0. Add 6 electrons for the nitrido, plus 3 2-electron donors for the amidos. 6 plus 6 equals 12 electrons total. All right, what about the tantalum compound? Well, the tantalum compound, you can see here, features 3 alkyls. I've circled one right here, but it also contains an alkylidine, which I'm indicating with the arrow. The alkylidine is a dianionic 4-electron donor, and so if we give the electrons back, we get a carbon, which has a hydrogen, a terp-butyl group, and 2 lone pairs on it. That is a 2 minus ligand overall. Carbon has 4 valence electrons, minus 4 lone pair electrons, minus 2 bonds, is 2 minus overall, and it is a 4-electron donor. And so each alkyl we know then is minus 1. That means this is 2 minus. That means this is tantalum 5, tantalum 5, which is D0, 4 electrons for the alkylidine, plus 3 2-electron donors for the alkyls. That gives us 10 electrons total. This tantalum compound is a 10-electron compound. All right, but there's other compounds, very commonly also other nitrogen-bound ligands that also can contribute multiple bonds to the transition metal center. And these are known as amidos. If you have an Nr 2 minus group, so amidos, Nr 2 minus, and so we're talking about a ligand that looks like this when you give the electrons back, 2 minus. And so these are dianionic. If they are bent, they are 4-electron donors, and the reason for that is the nitrogen atom is sp2 hybridized, and the lone pair is pointing in the other direction. If they are linear, though, in which the nitrogen center is now sp hybridized, if it is sp hybridized, that means there is a lone pair in a 2p orbital. If the transition metal center has a low electron count and it is linear at nitrogen, the lone pair on the nitrogen center can donate in a pi fashion to the empty orbitals on the transition metal center, contributing now not 4 electrons, but rather 6 electrons. And so you can sort of draw a resonance structure, and often you see it drawn as such, in which the amido, if it is linear, is drawn as a triple bond to the metal center, representing the fact that it is a dianionic 6-electron donor. All right, well, let's now electron count 2 such examples. And so over here I have a tantalum compound in which the nitrogen center is almost sp2 hybridized. sp2 is approximately 120 degrees. The angle at this nitrogen is 116, so it's pretty much sp2, which means it's pretty much bent, and so it is going to be a dianionic 4-electron donor, and so we have a 2 minus. Notice that if you give the electrons back to this nitrogen, you get a glorified Nr2 minus again, so it is an anionic ligand. Chloride, you know, is anionic, and this is Cp star. Cp star is just like Cp, but rather than having just hydrogens, all of these groups are actually methyl groups. It doesn't affect the electron count, but typically Cp star compounds are more stable, and so we have a -1, a -2, a -3, and a -5. And so tantalum is tantalum 5. Tantalum 5 is D0, plus 6 electrons due to the Cp, plus 4 electrons due to the amido, plus 4 electrons due to the 2 2-electron donors. This gives us a 14-electron tantalum compound. Let's go to the olefin metathesis tungsten 6 compound shown on the right. Notice that here our amido is linear. The nitrogen center is sp hybridized. That means that this lone pair on nitrogen can donate to the transition metal center. We're going to see here that the tungsten center is tungsten 6. It is D0, and so this d pi orbital I've drawn up here is in fact empty. And so this is, again, this is 2 minus. This is an alkylidine, which is 2 minus, and alkoxide is 1 minus, and pyrrole here has a lone pair that's not drawn. When you give the electrons back, it is essentially an Nr 2 minus donor, and so we have an overall 6 minus due to the ligands. The compound is neutral, so it is tungsten 6, which is D0, plus 6 electrons due to the linear amido, plus 4 electrons due to the alkylidine, plus 2 2-electron donors. We add this all up, we get a 14-electron tungsten compound. What about some other ligands, commonly ones that give us problems, give us headaches, they're ambiguous, and they can be a little bit tricky? I've put group 3 into this category, and there's a couple more on the next page. Bound acetonitrile, this gives everybody lots of problems. When you give the electrons back to this nitrogen, it is a nitrogen featuring 3 bonds and a lone pair. It is neutral. Any bound acetonitrile being a pretty common solvent, is a neutral 2-electron donor. Something that really screws people up is a isomer of that, isonitriles. And so if you give the electrons back to this carbon center, notice that you have a carbon center featuring a triple bond to nitrogen that has a lone pair on that carbon atom. That carbon atom then is anionic. However, pay attention to the nitrogen atom. The nitrogen atom itself has 4 bonds. That means it is positively charged. 5 valence electrons, no lone pairs, minus 4 bonds, it is positively charged. And so this overall then, the negative and the positive cancel out. This is a neutral 2-electron donor. And so another one to consider is ligands that are based on a boron that is 4-coordinate. And so I've kind of drawn out a schematic here. So if you encounter a ligand in which there's a boron in the backbone that is 4-coordinate, that boron is negatively charged, so you have to account for that. And I'm going to show you a couple examples here. And so the 4-coordinate boron is negatively charged. Remember, boron has 3 valence electrons, minus 4 bonds equals -1 overall. All right, and here is now 2 different compounds. Notice here we have actually a dimer. And so if I cut this dimer in half right here, notice if I give the electrons back, this is a P with 2 isopropyls and 2 lone pairs. This is a PR2 minus. This is a bridging phosphido. It can give electrons in both directions to both nickel centers. So this is a -1. The other phosphido is a -1. Chloride is -1. Other chloride is -1. But if we're thinking about this nickel center that I'm circling, there's a phosphido and a chloride, and so it is nickel 2, which is D8, 2 electrons from the isonitrile, 2 electrons from the bridging phosphido, 2 electrons from the other bridging phosphido, 2 electrons from the chloride. That's 4 different 2-electron donors contributing 8 more electrons for 16 electrons total. All right, what about this platinum compound on the lower right-hand corner? Notice that the platinum complex itself is an overall anionic. It features a cation as a counterion. And so the overall charge on this complex is going to be -1. Notice that we give the electrons back, Both of these methyl groups are negatively charged. Give the electrons back. These nitrogen donors are neutral. However, there is a boron in the backbone that is 4-coordinate, so it is anionic. So I have 3 minus charges. I have my platinum center. It was overall -1, and so the platinum center therefore must be +2. So this is platinum 2. Platinum 2 is D8. There are 4 2-electron donors contributing 8 more electrons for 16 electrons total. Sorry, this is bad looking. 16 electrons total. 16 electrons total. All right. The last one that I want to talk about that's a little bit ambiguous is N-heterocyclic carbenes, commonly abbreviated as NHCs. They are typically drawn in 2 ways, and it can just vary wildly. They're either drawn like this, or they are drawn with the swoop. The swoop represents the fact there is a delocalization of electron density. However, N-heterocyclic carbenes, whether they are drawn with or without the swoop, so here is without the swoop, here is with the swoop, they are neutral 2-electron donors. When you give the electrons back, you get this, which is an N-heterocyclic carbene. Notice that this carbon center, even though it does not have an octet, it has 6 electrons total around it. It has a sextet. If you were to calculate the formal charge, 4 valence electrons minus 2 electrons minus 2 bonds, it is a neutral 2-electron donor. So what's the deal with the swoop? Well, remember that these nitrogens are sp2 hybridized and feature lone pairs. You can take either nitrogen center and actually dump the electron density into the NC bond, creating an NC double bond. That'll then create a negative charge on the carbon center, but a positive charge on the nitrogen center. Therefore, it is still neutral. You could have also chose this nitrogen to dump the electron density in, and then you'd obviously have to open up and reform the lone pair on the other nitrogen center. However, in both cases, it doesn't matter. The N-heterocyclic carbenes are neutral 2-electron donors. If you see a metal bound to a carbon that is in a 5-membered ring featuring flanking nitrogens, these are N-heterocyclic carbene donors. Again, these are neutral 2-electron donors. All right, let's do some examples. And the 2 examples I have here, I really like because they kind of encompass a lot of what I've been talking about. This iron amido bisamido compound that was reported in Science a couple years ago, and this nickel compound shown down here. Well, what I really like about these compounds is notice that the iron compound on the left is cationic, and so we're going to have to account for that when we're electron counting. It features 2 NHC donors. It features a 4-coordinate boron in the backbone, which we know is going to be negatively charged, and it features 2 different linear amidos shown here. Both of these linear amidos are both 2- 6 electron donors. 2- 6 electron donors. So let's electron count this compound. We also have, so again, the NHCs are neutral 2 electron donors. The boron is negatively charged. So we have -5 due to the ligands, plus the charge on the metal center must equal +1 because this is a cationic compound. So X is +6. This is a highly unusual iron 6 compound, which is D2. Notice that we have 12 electrons due to 2 separate linear amidos plus 2 electron donors due to the N-heterocyclic carbines. This gives us 18 electrons total. I really like this nickel compound on the right as well. Again, we have NHC donors that are neutral 2 electron donors. But notice we have a bent amido in this case. The nitrogen is not linear. It is sp2 hybridized. It is a dianionic 4 electron donor in this case. And so the overall complex is neutral, and so it must be nickel 2. Nickel 2 is D8 plus 4 electrons due to the bent amido plus 4 electrons due to the 2 N-heterocyclic carbines. This is a 16 electron compound. I should mention that this kind of swoop action is not just reserved for N-heterocyclic carbines. You see this in lots of ligands that feature a delocalization of electron density, which is often commonly seen in what is known as knack-knack ligands. And so knack-knack ligands are often drawn. You can see the swoop is drawn right here. And so what that represents is the fact that there is 2 competing resonance structures. I've drawn them below. And so all this means is that one of the nitrogen donors you want to consider to be anionic, and the other nitrogen donor you want to consider to be neutral. Both donate 2 electrons. So if one is anionic and donates 2 electrons, so this is anionic and contributes 2 electrons. This is neutral and contributes 2 electrons. That means overall it is a -1 4 electron donor. And so you can obviously jockey between the 2 different resonance structures by just pushing electron density, and that'll get you over here. And so I just want to make that clear. Anytime you see the swoop, you have to parse through it a little bit to figure out what the actual charge and total electron count due to the ligand is. And so what we know now is that one of the nitrogens is negative, the other is neutral, chloride is negative, so it must be iron 2. Iron 2 is D6. You then have 3 2 electron donors total that contribute 6 more electrons. This is a 12 electron compound. And so this is kind of just the beginning of all the electron counting. You can definitely practice more, and in a subsequent lecture, I'm going to actually do a whole bunch of problems. I'm just going to quickly go through them, but I'm going to quickly step-by-step go through them. So hopefully you can figure out how to electron count. Once you know how to electron count, you're on your way to understanding organometallic chemistry. And as far as I can tell, that's a great thing. All right.